Hello everyone, welcome to lecture 17 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on the optical properties of metals and dielectric. It's basically a continuation of the previous lecture. So, in this one we will briefly look into the optical properties of metal that we have described earlier based on Drude model. We will take up the dispersion relations of bulk plasmons, and we will discuss other dispersion relations example in details, and we will also look into the optical properties of other dielectric materials. So, this is what we have seen earlier, that the Drude model, the permittivity can be described as epsilon omega, which is 1 minus omega p square by omega square plus I gamma omega. So, omega p is basically the plasma frequency, which is given as square root of n square by m epsilon naught. And in this particular model, if you separate out the real and the imaginary part, you will get epsilon 1 and epsilon 2, and this is how you can write them. Epsilon 1 is 1 minus omega p square divided by omega square plus gamma square, whereas omega 2 is gamma by omega times omega p square divided by omega square plus gamma square. Now, this is how you can plot it. So, you can say at omega equals omega p, okay, the permittivity, so you can put this if there is no damping involved, okay, you can say that at omega equals omega p your permittivity becomes 0, something like that. Okay. So, what do you understand, that when the frequency is below the plasma frequency, okay, so the permittivity is negative. So, that is where the metals retain their metallic characteristics, the metal will be reflective. But for larger frequencies which is close to plasma frequency, we will see that the product omega tau will be much greater than 1, that leads to negligible damping. So, in that case you will understand that this particular term will become predominantly real, and you will have epsilon omega equals 1 minus omega p square by omega square. Okay. So, you are basically ignoring the damping in this particular case, and that is what is typically plotted here, right. So, you can take this as a dielectric function of undamped free electron plasma. So, this is what the expression will look like, 1 minus omega p square by omega square. So, understood that this is in the case when damping is not there. So, typically the relaxation time tau is of the order of 10 to the power minus 14 second, that will give you a gamma which is around 100 terahertz, okay, and that is 0.4 electron volt. Okay. The mass of the electron is 9.1 10 to the power minus 31 kg, epsilon naught is 8.85 into 10 to the power minus 12 farad per meter. This is the vacuum permittivity, and is the electron concentration. So, typically you have 6 into 10 to the power 28 per meter cube for gold and silver, and elementary charge of electron is 1.6 10 to the power minus 19 coulomb. So, these are all constants that you should be knowing. So, with that what we understood, that this is the region which is of vast interest, because below which it behaves like a shiny metal. Beyond this frequency the metal will become transparent, right. So, this is what we will be considering, that for very low frequencies where omega is much lesser than 1 by tau, that is your gamma frequency, okay, 1 by tau is nothing but gamma, the damping frequency. In that case you will see that the damping is much larger. So, your epsilon 2, that is nothing but the imaginary part of the permittivity, will be much larger than the real part. Okay. So, in that case you can always try to write the relative permittivity, okay, epsilon r, say you write it in the real and the imaginary part. You can also take this as epsilon 1 and epsilon 2. Why I am giving all these different notations, because in different books they go with different kind of notation. Some goes with this kind of prime and double prime kind of notation. Few books they write with epsilon 1 and epsilon 2 kind of notation, that is absolutely fine. So, this is the relative permittivity, and this is basically complex. So, you can write it as n plus I kappa whole square, where n is basically the real part of the refractive index and this is giving you absorption coefficient, right. So, n and kappa, they are nothing but square root of epsilon 2 by 2. So, epsilon 2 is basically epsilon r double prime, that is the same thing. You can put these values in this particular regime. So, you are getting square root tau omega p square by 2 omega naught. There are other correlation or relationship that can relate this real part and the imaginary part with n and kappa. Okay. In few books you will also see they are written as n1 and n2, those are all fine. Okay. The real part of the complex refractive index can be written as n, the imaginary can be written as kappa or k. Okay. So, if you do n square minus kappa square, that is giving you the real part of the permittivity, and when you do 2 n k or 2 n kappa, that will give you the imaginary part of the permittivity. Now, in this region where the damping is high, the metal is mainly absorbing. So, there is an absorption coefficient which is alpha, that is given as square root of 2 omega square tau omega by c square. Now, if you introduce the DC conductivity, that is sigma naught in this expression, you will see that sigma naught is given as n square tau by m. So, which is basically omega p square tau epsilon naught. Okay. So, if you do the substitution here, you will see alpha can be written as square root of 2 epsilon naught, alpha can be written as square root 2 sigma naught omega mu naught. Okay. So, c square is nothing but 1 by c square is nothing but mu naught epsilon naught. So, you can use that and find out what is this alpha, that is the absorption coefficient, right. Now, the application of Beer-Lambert's law of absorption would imply that for low frequencies, the field will fall off inside the metal following a relationship which is exponential decay given by e to the power minus z by delta. Delta is nothing but the skin depth. So, delta is related to the absorption that we have seen earlier. So, delta is 2 by alpha, which is also written as c divided by kappa omega, okay, and it can be given as square root of 2 divided by sigma naught omega mu naught. So, this is skin depth, right. Now, when you move to higher frequencies, something like you go for omega tau, which is much larger than 1, but smaller than the omega p tau. So, when you are here in this region, you will see that the complex refractive index is predominantly imaginary. So, that means it is going to give you a reflection coefficient r that is equal to 1, and the conductivity sigma will acquire more and more complex character. So, that will basically blur the boundary between the free and the bound charges. So, our discussion up to this point has assumed ideal free electron metal, but now we will briefly compare the model with an example of real metal, which is important in this field of plasmonics. So, in the free electron model, you can put this epsilon going to 1 when the frequency is much larger than plasma frequency, right. We have seen that. So, for the noble metals gold, silver, copper, you can use an extension of this model, okay, that is needed for the region when frequency is much larger than omega p, where the response is mainly dominated by the free electrons, right. So, in that case, the residual polarization which comes due to the positive background of the ion cores can be described by adding a term something like p infinity, that is equal to epsilon naught epsilon infinity minus 1 times E. So, here the p represents the polarization due to the free electrons, right. So, what we are seeing here, that this effect is therefore described by a dielectric constant for high frequency, that is this particular term epsilon infinity. So, typically this is a constant that ranges between 1 to 10, and you can use this as your high frequency dielectric constant. So, you can modify your permittivity values for gold, silver and copper to be epsilon omega which is epsilon infinity minus omega p square divided by omega square plus I gamma omega. So, this model you can use in the case of gold, silver, copper. Okay. You cannot use 1 here because of this particular reason. Now, the validity limit for the electron description can be seen here, that for this particular energy range, the value this model, which is the solid line, matches very well with the dotted lines. Here also you can see, but beyond a particular point, okay, the interband transitions take place, and that basically limit the validity of this model, typically at visible and other higher frequencies, right. So, below that it is doing a good job, but after this, like in the visible and the higher frequency range, because of the interband transitions, it is failing. Okay. So, this is the dielectric function of the free electron gas, which is the solid line, fitted to the literature values of the dielectric data of the gold, which is obtained from the Johnson and Christie paper in 1972, right. So, now let us look into the dispersion relations of different plasmons. Okay. So, let us start with the bulk plasmon. So, the physical significance of excitation at the plasma frequency would be to let us consider the collective longitudinal oscillation of the conduction electron gas versus the fixed positive background of the ion cores in a plasma slab. So, this is the amount of displacement. So, you can see the positive conductivity will be sigma equals plus n e u, u is the amount of displacement. So, here it will be minus n e u. So, this is nothing but longitudinal collective oscillation of the conduction electron of a metal. So, what you see here is called volume plasmon or bulk plasmon. So, this is coming from a collective displacement of the electric cloud, which is displaced by a distance of u, that has led to this surface charge density, which is sigma, and that you can write as plus NEU on this side, okay, and that is because of the electron cloud has moved away. Okay. So, this is happening at the slab boundaries. So, the electric field inside the slab can be written as E, which is sigma by epsilon naught. You can understand the restoring force that can be applied on the electron. F can be written as minus E minus small e capital E. So, this is the electric field, this is the charge of the electron. The equation of motion is pretty simple here. M x double dot will be minus n e square by epsilon naught into x, the amount of displacement. So, here it is u, or you can also take it as x, that is fine. And from this you can obtain what is also called the plasma frequency. Okay. So, plasma frequency will be square root of n e square by epsilon naught m. So, here you can see the plasma frequency is mainly dependent on the electron concentration, electron charge, vacuum permittivity and the mass of electron. So, this is pretty much the material dependent parameter. Now, if you turn to a description of transparency region, which is supposed to be at a frequency much larger than the plasma frequency of the free electron gas model, you will see that the dispersion relation of the travelling waves can be obtained as omega square epsilon r equals c square omega square, and epsilon r we have already written as in the range of transparency, it will be 1 minus omega p square by omega square. Okay. So, if you put this guy here, okay, you will see that you will obtain a relation of omega square equals omega p square plus k square c square, right. So, if you try to plot this as a function of frequency and wave vector, both normalized with plasma frequency. So, the frequency axis can be written as omega by omega p, wave vector can be written as kc by omega p. So, this is basically a light line, okay, to omega equals ck, that is the light line. So, if you take epsilon r equals 1, you get the light line, and this is for the plasma dispersion. So, you can obtain the equation as omega square minus omega p square equals k square c square. So, this is how it looks like. So, this is the dispersion relation of a free electron gas okay, and the electromagnetic wave propagation is allowed only for omega greater than omega p, right. So, this is for free electron metal, right. Now, as can be seen that when you have omega less than omega p, okay, so that is here the propagation is not allowed. You can only propagate when your when you have omega greater than omega p. So, below this the propagation of the transverse electromagnetic wave is basically forbidden inside the metal plasma. So, if you have something more than omega p, that is good. Okay. So, the plasma then supports the transverse wave that can propagate inside the material with a group velocity that is given as Vg, which will be nothing but the slope of this curve, that is d omega by dk. Okay. So, and that will be less than c. So, this slope is obviously less than the light line. So, you will have a slower moving wave in the material. Now, the significance of this plasma frequency can be further elucidated by recognizing that in the small damping limit, when you consider epsilon omega p equals 0, that means for k equals 0, the excitation must therefore be a collective longitudinal mode. So, in this case you can write d equals 0, which is nothing but epsilon naught E plus p, right. And from this you can understand that the plasma frequency at plasma frequency the electric field is basically nothing but the depolarization field, because electric field will be simply given as minus p by epsilon naught, right. Now, let us take some further examples of this dispersion relations. Okay. So, when you have free space, you can write epsilon r equals 1. So, you can put this equation k equals square root epsilon by c into 1. So, this is 1. So, you simply have omega equals c k, that is basically your air or light line. When you have epsilon equals 2, that is in silica. So, this equation will become k equals square root of epsilon by c into omega. So, that means omega will be 0.7 c k. So, this is how the slope of the curve reduces. Okay. So, here you assume the silica to be non-dispersive and it has got a refractive index that is same throughout all the frequencies. Okay. For the metal, your epsilon omega can be written as 1 minus omega p square by omega square. So, that gives you, you put it back into this equation, you get k equals omega by c square root of 1 minus omega p square by omega square, that gives you this particular dispersion relation, that is omega square minus omega p square equals c square k square, right. Now, we have also seen that the group velocity is slower than c. So, you are having a slow group velocity. Also, it can allow longer wavelength. Okay. K will be larger than k naught. So, asymptotically you can see that this basically approaches the light line as omega is approaching infinity. So, in this particular axis, just to remind you, this is at the normalized frequency and this is the normalized wave vector. So, it is a omega k graph. Okay. So, it is c k by omega p, this is the value here. So, now let us look into the optical properties of dielectric materials. Dielectrics are by far the dominant materials that are used for optical components and devices. In conventional optical systems, almost all functional parts except for the reflection surfaces are basically made from crystalline and glassy materials. The reason is simple, that light is effectively manipulated only when it is efficiently passing through a medium, meaning that the medium should be to at least some degree a dielectric. The underlying physical background of light interacting with a dielectric can be analyzed by using Maxwell's equation plus the two constitutive relations we have seen. So, you can use these particular equations. Okay, here the first equation tells you the relationship between the electric displacement, the electric field and the polarization density P. So, we have already seen how to write that, epsilon naught 1 plus chi e into E, which is epsilon naught epsilon r into E. Okay. So, here epsilon naught is the vacuum permittivity, this is the relative permittivity. Similarly, you can also have the relationship between B, H and M. So, we have seen earlier. So, this can also be written as mu naught mu r and H. H is the magnetic field and B is the magnetic flux density. So, the study of the linear interactions between light and matter, especially which involves determining the solutions to Maxwell's equation, will be by using these constitutive relations along with appropriate boundary conditions. So, at optical frequencies, you can see that the magnetic susceptibility chi m in any conventional material typically vanishes. So, you can safely assume the relative permeability mu r to be 1 in all those cases. So, this condition simplifies our description of the optical materials, which are basically transparent ones, to be very particular. So, we can simply take refractive index to be n, which is square root of epsilon r, because mu r is always 1. So, even though all media are dispersive and absorbent in a very strict sense, the use of real numbers for the refractive index makes it very convenient, and therefore, that has become a standard practice in the design and analysis of optical components and devices, right. And particularly when you think about refraction and reflection behavior of dielectric systems, including magnitude and phase information, these are well characterized by a set of Fresnel equation we have already seen. These are simple algebraic formula that are based on the refractive indices and the incident angle as variables, but that describes the reflection and refraction from different interfaces of different medium, right. Now, although the refractive index of isotropic, homogeneous and linear dielectric material can be viewed as a real number in many cases, we should note that a rigorous treatment of light interacting with optical media, one need to consider the frequency dependence. Okay. So, typically at optical frequencies, the oscillation of the electric field is so fast that the bound electrons in atoms or molecules are usually unable to follow the electric field in time. So, consequently, you can think that the equation D equals epsilon naught E plus P, which earlier we wrote as epsilon naught 1 plus chi E times E, that has given us the relative permittivity. This particular equation does not hold good in time domain for high frequencies of the optical range. Instead, the electromagnetic response of the medium should be better described as a function of time, considering dt, okay, because it not only depends on the electric field at that moment, but also on the electric field of all past times. So, ideally the constitutive relationships should take into account this time operator or the convolution, and the equation should be written as dt equals epsilon naught E t plus epsilon naught integration from minus infinity to tau chi e t minus tau e tau d tau. Okay. So, this is how you should actually get the constitutive relationship at optical frequencies. Now, fortunately, the proportionality is still valid for the relationship between D and E in the frequency domain, as long as the material is considered to be a linear medium, right. That means, the susceptibility remains independent of the strength of the electric field in such a medium. So, you can safely write the frequency domain constitutive relationship as d omega, which is epsilon omega E omega. So, epsilon omega you can write as 1 plus chi E omega, right. So, this is the relationship in the frequency domain. Now, why we are bringing the dependence on omega? Because most materials, or we will see that metamaterials, which are basically metal dielectric composite units, they are strongly dispersive. That means, their property depends on the frequency. So, in the visible or near infrared wavelength range, the origin of the dispersion in a metamaterial can be mostly ascribed to the metallic part, because metal are much more dispersive than transparent dielectric medium. Nevertheless, it is helpful to study the frequency sensitivity of the dielectric function epsilon omega in dielectric medium, and in particular when we extend our interest to the whole optical spectrum from say near UV to mid infrared, which are ranging from 200 to 400 nanometer to tens of microns. The dispersion of even the best transparent material can also be no longer becomes negligible for such a wide range. Okay. You can think the same for the microwave frequency also, that range, that at different frequency the material may behave slightly differently. So, you should always take into consideration the dispersion. The transparency window for most dielectric material is bounded at the long wavelength side by the infrared absorption mode of the phonons due to the lattice vibrations, while the high frequency side, okay, the window is bounded by the interband electron hole transition. So, one side you have low frequency, that is coming from the infrared absorption of the phonons, which are mainly coming from the lattice vibration. On the high frequency side or the short wavelength side, that is also bounded by interband electron hole transitions, right. So, the approximate spectral transparency ranges for a number of important dielectric materials you can see here, starting from alumina, calcite, barium fluoride, zinc selenide, zinc sulphide and so on. So, this is the spectral range given in micrometer, this is the wavelength, and this is the UV, visible, infrared, mid and far infrared. So, this range tells you the transparency range. So, when designing an optical metamaterial, it is important to make sure that the selected dielectric constituent is basically transparent within that wavelength range of interest. So, that is where you can refer to this particular chart. If you do not do that, there will be substantial loss arising from the electron or absorption or say phonon resonances in the dielectric, which are not good for the metamaterial performance, right. So, the dielectric function, your epsilon omega, can be expressed in a classical Helmholtz-Drude model in the form of epsilon omega equals 1 plus summation over j s j omega j square divided by omega j square minus I omega gamma j. So, here omega j is basically the resonance frequency of the jth mode, s j and j basically represent the strength and the damping constant of the jth mode, right. So, you can see that you can obtain, there are different modes associated in a particular dispersion range, okay, or dispersion relation. So, a typical frequency dependent permittivity of a usual transparent material, dielectric material, can be seen like this. So, here it is transparent completely in the visible range, in the ultraviolet and also in the infrared it is absorbing strongly. Okay. So, you can see that these resonances can be included in this oscillator formula with omega 1 that represents the phonon resonance in the mid infrared, okay, that is basically from the lattice vibrations or and you can see omega 2, that is another one that tells you about the electron transition in the ultraviolet range due to the band gap of the crystal, right. So, the dielectric function here oscillates a Lorentz line shape at each resonance along with distinct peak that you can see in the imaginary one. So, the red dotted one is showing the imaginary part of the permittivity, which is referring to the loss, significant loss associated with the resonance, and this figure tells you that between these two resonant frequencies the permittivity curve is rather flat and it has got a negligible imaginary part, and this is where exactly you should be operating for that particular for making optical metamaterials. So, if you take the common dielectric like quartz or alumina, this is the reason why they appear transparent to the visible light, but they are not in the infrared and the ultraviolet region, right. So, with that we will conclude this lecture. So, if you have got any query regarding this lecture, drop an email to this email address mentioning the subject and the course number on the subject line. Thank you.